welcome to this event. Today we have Dr. Clare Eayrs from the Center of Global Sea Level Change at NYU Abu Dhabi. It's a pleasure to have Clare here with us today. Some background on Clare. She did her PhD. Sorry about the noise, but there's construction behind me. She did her PhD in the UK, then she worked with the UK government in ecosystem modeling, effectively providing science advice for policy. A few years ago, Clare joined us all here at NYU Abu Dhabi, and she's been working on the ice part of the climate system, particularly sea ice, which she will talk about today. Another thing to mention about Clare is that she's been very active in science community support through the WMO, the World Meteorological Organization, supporting young scientists and advancing people's careers. But let's get on with the talk. And one other thing I want to mention is that some of you may find it curious that we talk about sea ice and do research on that at NYU Abu Dhabi. And I think Clare will bring this point out, but I want to bring it out myself, that we live on obviously a very small planet, which is undergoing some change. And one of the largest and first changes we'll see is the loss of ice. And so things that will change in Abu Dhabi will first probably come from Antarctica and changes in ice. So that's why we're focused on that research. So Clare, if you're there, and I'll pass the baton to you now, and off we go.
Thanks very much for the introduction, David. And thank you for the Research Institute for inviting me to speak here today. So as David introduced, I'm a researcher at the Center for Global Sea Level Change here at New York University, Abu Dhabi. And the aim of our center is to combine observations and computer models to understand past sea level rise and to project how it will change in the future. Now, sea ice cover plays a critical role in the climate system, and understanding changes in the global sea ice cover is an important aspect of the work that we're doing at the center. In this talk, I'm going to introduce you to sea ice, explain why it's important to the global climate. I'm going to describe how we observe and study it, and present some of the highlights of my research into sea ice. So to get going, what is sea ice? I'm sure you've all seen plenty of articles in the news about melting ice in the polar regions. So lots of these articles are referring to ice, but this can either be land ice or sea ice, and they're really quite different to each other. We use the term land ice to describe icebergs, glaciers, ice sheets, and ice shelves. So basically anything that's formed on land or has broken off from the land. But today I'm going to be talking about sea ice, and this is the ice that's formed when the ocean freezes in winter. So sea ice is simply frozen seawater, and it forms, grows, and melts in the ocean. And it occurs in both the Arctic in the North Pole and around Antarctica at the south. So how does it form? Well, ocean water freezes just like fresh water, but at a lower temperature because salt in the ocean lowers the freezing point. And as you have more salt in the water, the freezing point lowers. The saltiness of ocean water varies around the world with temperature, evaporation, and precipitation, but its freezing point tends to be around -1.8 degrees Celsius. So each winter, as the ocean water begins to get to -1.8 degrees, we start to get something called frazzle ice, these small needle-like ice crystals that start to form in the water column. This is a photo of some frazzle ice. These ice crystals are typically about 3 to 4 millimeters in diameter when they start to form. And then they start clumping together to form this kind of slush that you can see in the picture here. What's quite important is it's only the water that freezes. So we've got salt water freezing, but the ice crystals eject the salt out of their crystalline form into the surrounding water. So you get higher salinity in the ocean around the sea ice. Some of the salt can become trapped in small pockets between the crystals. They start clumping together. So if you were to taste sea ice, it would actually taste slightly salty. I don't necessarily recommend that because obviously whatever else is in the ocean can also be in these brine channels. But the point is that the ice is fresh and it can contain pockets of salty water. Once we've got the frazzle ice, then the way that ice continues to form depends on the ocean conditions. So if we've got calm conditions, low winds and currents and no waves, then the frazzle ice starts to join together and form a thin, smooth layer of ice called grease ice. And you can see from this picture why it's called grease ice, because it really resembles an oil slick. The grease ice develops into a continuous thin sheet of ice called nihilus. And initially this sheet is very, very thin and dark, but it becomes lighter as it thickens, eventually thickening into a much more stable sheet called sheet ice. And this ice continues to thicken from underneath while the ocean stays cold enough to freeze. In this image here, you can see that the sea ice has got a snow cover and it's thick enough for people to be working on. So that was calm conditions. If we have rough conditions, so wind, waves, currents disturbing the ocean surface, then ice formation takes place via something called the Pancake Cycle, in which the fragile ice clumps together to form pancakes, so-called because they look like pancakes. And the signature feature of this type of ice is around the edges, you can see these raised ridges. And that happens because these pancakes are all bumping together as the waves move around the ocean. Eventually, the pancakes cement together and consolidate into sheet ice. So both ways we can get proper pack ice forming. So on average, sea ice covers about 25 million kilometers squared. So this is about 15% of the world's ocean that can be frozen at any one time. And this is an area about 2.5 times the size of the United States. But there is a big seasonal change in sea ice cover during the year. Obviously, the hemispheres are in opposite seasonal phases. So when it's summer in the Arctic and ice is melting, it's winter in Antarctica and ice is growing. So why study sea ice? There are many reasons to study sea ice, and I'm sure a lot of you are thinking, why would you study sea ice in Abu Dhabi? Surely only people in polar regions need to study sea ice. But actually, it is very important for a research centre like ours that is studying sea level change to know what's happening with sea ice. So sea level change is a consequence of warming climate, and sea ice plays a critical role in that climate system. Even very small changes in the atmosphere and the ocean can dramatically alter the yearly cycle of sea ice melt and growth. So any changes in sea ice are representative of cumulative changes taking place in both the ocean and the atmosphere. The main role that sea ice plays in the climate system is in reflecting solar radiation back into space. And a measure of how much radiation is reflected by a surface is called albedo. The word albedo is derived from the Latin word albus, meaning white. And white snow and ice tend to have much higher albedo than, for example, soil, forests, and open water. So open water actually absorbs most of the solar radiation, whereas if you have in particularly very white snow on the top, then nearly everything is getting reflected back into space. You're going to hear me mention albedo quite a few times in this talk. It is really important. The high albedo reflects much of the incoming solar radiation in polar regions, and that keeps them much cooler than if it was an ice-free environment. And this albedo effect can lead to a self-reinforcing feedback loop. So for example, if you have an initially slightly warmer climate, then following this ice albedo feedback, then we'll have less ice, which will lead to increased warming and even less ice. On the other hand, if we've got initially cool, then you would have colder temperatures and more ice forming. That would lead to even more cooling and even more ice formation. And with these feedback cycles, the ice cover can amplify even quite small climate changes. One thing to remember, though, is that in winter, there's no light or very little light reaching the polar regions. So for sea ice, this feedback is really only important in the summer, and changing albedo in the summer is really important for the polar regions. Over geological time, the temperature of the Earth has changed. And if we go back millions of years, we find that the Earth has slowly fluctuated between two different states that we call greenhouse Earth and Icehouse Earth. While the distribution of the continental masses has played a key role in these changing states, the ice albedo feedback also plays a part. So in this figure here, here 0 is where we are right now. And this part of the axis is going back in time over millions of years. So this is 80 million years ago. And at the top, we've just got current time. This is where we are here. And this scale is slightly different. This is hundreds of years. And so what you can see is that so 40 to 80 million years ago, we had something called a greenhouse world. And then ever since then, the world has been slowly cooling until we get to the stage that we're in now, which we call an icehouse world. So what's a greenhouse Earth? So during a greenhouse interval, there's no ice at the poles, so there's no ice at all. And the Earth explodes with life. The Cambrian explosion 540 million years ago occurred during a greenhouse Earth state. There is something called a hypothetical hothouse Earth, which is an irreversible tipping point corresponding to the ongoing runaway greenhouse effect on the planet Venus. So Venus has currently got very, very high concentration, almost 97%, I think, carbon dioxide. and the rest of their atmosphere is nitrogen, and they have temperatures of over 400 degrees Celsius. And there's been some recent research discussing the possibility of our Earth system being on a hothouse Earth trajectory, so perhaps moving into this hothouse Earth. According to the last IPCC report, there is virtually no chance of this being introduced by anthropogenic activities. I'm not sure this will change in the upcoming assessment report that's due out next year, but there is certainly a lot of scientific debate going on right now about what are the critical thresholds for the sort of self-perpetuating feedbacks, such as the ice albedo effect. So right now we currently live in an icehouse Earth, so we've got ice at both of the poles. And within these icehouse periods, the Earth has shorter cycles of glacials and interglacials. So glacial periods, those are the times when we have ice sheets covering large parts of the continents. They tend to last about 80,000 years. And right now we're living in a mild interglacial. So the interglacial periods are when the ice retreats towards the poles. There is an extreme phase. So similarly, we had the hothouse Earth related to greenhouse Earth. There's an extreme phase of Icehouse Earth, something called Snowball Earth. And this has been seen actually in the geological records at least twice. The last of these occurred about 635 million years ago, just when complex life was starting to develop. And what happens with Snowball Earth is if you start getting sea ice to a low enough latitude, then you do get this runaway situation where you've got very cold, almost all of the solar energy is being reflected back into space, and it gets very cold and you get more ice forming. It's still uncertain if during these snowball effects, ice blanketed the entire planet, or if it was a little bit more like slushy and open in some areas, but certainly it would have been near global ice cover. The current distribution of the continents makes a snowball Earth unlikely to happen right now. So how do we measure sea ice? It's difficult to study directly because it's in such remote locations with extreme conditions. I'll tell you a little bit about some field ice studies that are going on, and I'll introduce you to some of my work a little bit later in the talk. But really, it's remote sensing that has been a game changer in our ability to observe sea ice. And I'll talk a little bit about the different ways we can observe it from space. We only have a 40-year record from remote sensing. And so an emerging area of research is to extend the satellite record using paleo records, in which we use fossils to understand where there was sea ice during geological times. So field observation. Well, people have been observing sea ice for various reasons ever since there have been humans living in polar regions. But historical records are really quite sparse, and any field observations that exist tend to be highly localized for short periods of time. Some of the best early records of sea ice extent, so it's telling us where the location of the ice edge is, actually come from whaling ships, and they date back to the late 1800s in the Arctic. However, these reports were not necessarily reliable because whalers had more interest in protecting their hunting grounds than being forthright with information on where the sea ice edge was. There's been various field programs through the years, but actually the most ambitious sea ice project of all time has just happened now in the Arctic. Was the Multidisciplinary Drifting Observatory for the Study of Arctic Climate Mosaic expedition. So in September 2019, the German research icebreaker, the Polish Stern, headed into the Arctic to spend a year trapped in the ice. So they deliberately got the icebreaker trapped in an ice floe. And the plan was to stay there for an entire year while taking measurements of almost anything they could possibly measure. Unfortunately, they didn't quite make a full year. They had to make a brief exit from the ice from late May to early June last year due to the coronavirus pandemic. But nevertheless, this program has collected an unprecedented legacy data set that will advance understanding and predicting of Arctic environmental change. And another really important thing about this expedition is it really demonstrated the strength of international collaboration. So it brought together funding from 20 different nations and participants from at least 37 nations. I want to share a story to highlight the challenging conditions that can be encountered when trying to navigate Antarctic sea ice. Sea ice played a key role in a legendary expedition to Antarctica that was led by Ernest Shackleton. So Shackleton and his crew sailed to Antarctica at the end of 1914 on their way to attempt the first land crossing of the continent on foot. Unfortunately, though, their expedition was thwarted by the harsh environment of the Weddell Sea. So in early 1915, the waters around their ship, the Endurance, froze, and the crew were forced to abandon the ship and they set up a makeshift camp on the ice. And they camped on the ice for quite some months. And after the ships finally sank in November 2015, they launched lifeboats, which they'd salvaged from the vessel. And they've made it to an island from which they eventually rescued in August 1916. Quite incredibly, not one life was lost. But we have a very good record of sea ice condition from Shackleton's journal. And here's a little tip from any of my book club members who might be joining the call. But if you do enjoy heroic tales of exploration, then I can highly recommend South, the story of Shackleton's last expedition. It's a blow-by-blow account of the trauma of getting a ship crushed in ice and how he managed to save all of the people on board. It's a really gripping tale of survival in the face of almost certain death. Now, last year, the WED-LC expedition 2019, two years ago, they planned to use autonomous underwater vehicles to search for the Endurance, which was possible because of the detailed measurements that the crew made at the time of the position of the ship when it finally sank. So what's an AUV? This is a photo of our Centres glider. This is not the one that they used in the expedition, but it's just an example to show you what these look like. It's an unmanned underwater robot that's controlled by an operator, usually on a vessel nearby. And the operator tells the submersible where to go, when to collect data, what kind of data should be sampled. So this expedition, the WED-LC expedition 2019, was on board the South African polar research vessel, the SA Agulhas 2, which myself and other members of our research group have been lucky enough to join. Unfortunately, like Shackleton before them, the team's well-laid plans were overcome by the rapidly moving ice and what Shackleton called the evil conditions of the WED-LC. The weather closed in and the sea ice conditions deteriorated. And unfortunately, the search for the Endurance had to be abandoned due to the risk of the Agulhas becoming trapped in the ice. So I just wanted to tell that story because even though we have much more advanced ships and equipment since 100 years ago, this really highlights the challenges of working in sea ice even today in this harsh, remote environment. Being able to observe sea ice from space has been a complete game changer for our observation record. So going to visit places in the sea ice, you can only go to specific locations and for short periods of time. There are a range of different ways that we can observe sea ice using remote sensing. So for example, we can see sea ice pretty well from space because it's really light white color, very different to detect from the surrounding ocean. But the disadvantage of visible imagery is that we can only collect visible data during the daytime, which is particularly a problem during winter in polar regions where there is little or even no daylight hours for part of the year. Another problem that you can see in this image here is that clouds obscure the sea ice, and polar regions tend to be cloudy, with clouds obscuring the images for about 70 to 90% of the time. Also, new ice is very thin and dark. Think back to that photo that I showed earlier on, and it's quite difficult to distinguish new ice from the ocean. We also can use sensors that measure infrared radiation. So everything on Earth is emitting heat. It's easy to detect sea ice because its temperature is generally much colder than the surrounding ocean. But again, clouds are a problem. Clouds also emit and reflect infrared radiation. And also, at the time of sea ice melting and sea ice formation, the temperature of the ice isn't necessarily that different from the surrounding ocean, so it can be hard to detect at those periods. It's really passive microwave that has really changed our ability to observe sea ice. So objects at the Earth's surface don't just emit infrared radiation, but they also emit microwaves at relatively low levels. And different objects emit microwave radiation differently. So one of the key things here is, well, for a start, we don't need daylight to be able to detect microwave radiation, but also more importantly, clouds don't emit much microwave radiation compared to sea ice. So the microwaves can penetrate the clouds and be used to detect sea ice during day and night, regardless of cloud cover. And this is really what's enabled us to be able to have this continuous 40-year record of daily sea ice. The major drawback to passive microwave radiation is that the energy level is quite low, so you have to collect over quite a large region. So the spatial resolution is generally quite coarse, but nonetheless, this is a very, very important record of observing sea ice. So in order to get around the low resolution of microwave radiation, we're starting to get active microwave sensors. So an active microwave sensor is just one that sends a ping down to the Earth, and then it measures how long it takes for that ping to come back off the surface. And in this image here, I'm just showing you a photograph of, an artist's impression of the IceSat-2 satellite, which is a laser altimeter. So it sends beams of visible light down and times how long it takes the pulse to come back. And with that, we can look at ice elevation. So this one here is looking at ice sheet elevation, but we can also see where there is sea ice. As well as laser altimeters, there's also radar altimeters, which work in the same way, but instead of using visible light, we use electromagnetic wave. And with these, this IceSat-2 was launched in 2018, and it's now collecting very, very high resolution. And it's exciting to see how this data will be used in the future to better understand sea ice. So what is it that we've observed at each of the poles? So I said before that sea ice forms at both poles and changes with the seasons, but it does behave quite differently between the North and South poles, and not just the fact that they're opposite in terms of their seasonality. Quite a lot of these differences are just due to basic geography. The Arctic is an ocean basin surrounded largely by mountainous continental land masses, and Antarctica is a continent surrounded by an ocean. So in the Arctic, in the winter, the sea ice extent is limited by the surrounding land masses, whereas in the Southern Ocean winter, which is the opposite season, sea ice can expand freely into the surrounding ocean. And then without a barrier, during the melting period, the sea ice can drift north into warmer waters. So nearly all of it is melted by the end of summer, whereas the Arctic has historically had sea ice in the center of the Arctic Ocean throughout the year. So Arctic sea ice, this is our poster child of climate change. Last year was a year of climate records, and I'm sure you've all seen media reports of hottest temperatures, most ever hurricanes, unprecedented wildfires, and Arctic sea ice saw its second lowest summer minimum. So I just want to show you just some short videos from NASA's Scientific Visualization Studio. So this one here is from January 1984 through to the end of 1985. And what you can see is how sea ice grows in the cold winter months before shrinking back again in summer. But the main thing to notice about this video is that a lot of the color that you can see is quite white. I don't know how well you can see the scale there, but that's telling you the age of the ice. So where we have very white regions, that means the ice is older than about 4 or 5 years. And you can see that there's a large portion of the center of the Arctic that always has ice in it. This is the same video, but this is 2017 to 2018. And the really key difference here is that you can see that the age of the ice has really changed. So we don't have such old ice anymore. And also there's quite large area of the Arctic Ocean that is now ice-free during the summer. Another way that we often show sea ice cover is in graphs, line graphs like this one here. So on the y-axis, I've got something called sea ice extent, which is a measure of how much sea ice cover there is. And this is just time, so January through to December. And sea ice increases to its maximum in about March in the Arctic, and then it melts to its minimum in about September, and then starts increasing again. And each of these new lines that's being drawn is just another year in the time series. And as you can see, Arctic sea ice has dropped every single month, but particularly in the September. So when will the Arctic be ice-free? The Arctic is warming nearly 3 times as fast as the rest of the planet. This rapid phenomenon is known as Arctic amplification, and it partly stems from rapid loss of sea ice cover. Remember the ice albedo effect I mentioned earlier? As the Arctic loses sea ice, energy from the sun that would have been reflected away by the bright white light is instead absorbed by the ocean, causing further warming. Now, there are various ways of defining what ice-free actually means, but the most common definition refers to a point at which Arctic sea ice cover at the end of the summer falls below 1 million square kilometers. And there's good reason for this. Arctic sea ice isn't just found in the central Arctic Ocean. So this definition of less than 1 million kilometers squared of sea ice cover means that the central Arctic Ocean should be completely ice-free, but with some remnants of sea ice persisting along the northern coastlines of Canada, Alaska, and Greenland. The date at which the Arctic will have its first ice-free summer has proved tricky to forecast. different climate models come up with a wide range of possible dates, but most suggest that it's likely to happen sometime around the middle of the century. So in the next 20 to 30 years, we should have ice-free Arctic. And the prospect of sea ice-free summers has got wide-ranging consequences. The commercial shipping industry follows sea ice forecasting research with keen interest, and the disappearance of sea ice in the summer would allow ships to find a new, faster route between the Atlantic and Pacific Oceans. Of course, increased shipping poses risks of its own. Think of the consequences of oil spills in hard-to-reach regions. And it's not necessarily going to be easy to increase storm activity without the dampening effects of sea ice. Will make these new routes quite difficult to navigate. Without the persistence of sea ice through the summer, there could be really strong implications for wildlife that utilize ice as a habitat. So both the top side and the underside of the ice provide places for animals to hunt, hide, rest, mate, give birth. And these changes could impact every level of the Arctic ecosystem, from plant algae growing on the underside of the ice to the polar bear, the region's top predator. The polar bears are an icon of climate change, as they're an early indicator because they're so dependent on the sea ice for hunting. And they also indirectly suffer the effects that their prey are suffering. Changes in species ranges and availability, as well as reduced access to various species because of unsafe ice, will create serious challenges to human health, food security, and possibly the survival of some cultures. Sea ice is transport infrastructure for many Arctic communities. So I showed you how sea ice has been changing in terms of how much ice there is in the Arctic, but there's also been significant changes in the timing of the melt and the freeze up, with an earlier start to the melting season and a later start to the freeze up. This figure here is just showing a change in the timing of freeze up between 1979 and 2019. So you can see that everywhere is it's getting later, but in some places where we've got the orange to red color, the freeze up is nearly a month later than it was 40 years ago. Slower freeze up in the fall leaves communities stranded for longer periods of the year and unable to access other communities, hunt for traditional foods, or travel for healthcare. There's also a growing field of research that suggests that changes to sea ice could be affecting weather, particularly in mid-latitude regions. I don't know if you've seen newspaper headlines talking about the beast from the east, but it seems that changes in Arctic sea ice are affecting the jet stream and the North Atlantic Oscillation. The key message really coming from the Arctic is that Arctic sea ice is decreasing, and that it doesn't only affect the people and the ecosystems that live there. So what of Antarctic sea ice? This has been my main area of focus over the last few years here at the Centre for Global Sea Level Change. And we've been looking at processes happening at the scale of individual storms through to how sea ice is changing on seasonal to interannual timescales. We've already discussed how sea ice in Antarctica isn't constrained by any continental masses. Each year, the ice grows from a minimum of less than 4 million kilometers squared in February to a maximum of nearly 19 million kilometers squared in September. And this annual change pretty much doubles the size of the continent. One thing that's particularly interesting about the differences between Arctic and Antarctic sea ice is the seasonal cycle. So this is similar to the figure that I showed earlier for the Arctic, but here we've got the minimum in February, and then it grows to a maximum towards the end of September, early October. In the Arctic, the cycle of melting versus warming is pretty much symmetrical, with 6 months of growing and 6 months of melting. And although I said that it's starting to have a longer melting season, however, in the Southern Ocean, there's a 7 months growing period, a bit longer than 7 months growing period, and a 5-month melting period, with most of the melt happening in just 3 months. This figure here shows the same information as this graph, but we're going from 1980 to 2018. And this is the sea ice concentration through the year. These are the days of the year. So this is January to December. And the dark colors are where we have this low sea ice extent, and the white colors are where we're getting maximum sea ice. And I've just noted here the time of the minimum ice extent and the time of the maximum ice extent. And what you can see is, unlike the Arctic, there isn't any trend in that, but there's huge variability from year to year about the timing of when it starts to grow again and the timing of when it gets to its maximum. But the really key thing is that even though there's large variability, sometimes a few weeks away from the average in terms of melt or freeze up, all years in the satellite record show a symmetry, and all of them have a longer growing period than a melting period. Another really interesting thing that we found is that there's a huge amount of variation in the melt rate, whereas the maximum growth rate doesn't change very much between years. In this scatter plot here, the black dots are from satellite, and the blue and the orange dots are from some model runs that we were using to look at this. And you can see that the black satellite matches pretty well with the model. And here, right, we've got the growth rate, so 200,000 kilometers squared per day, tends to be about what Antarctic sea ice grows at the maximum. And it doesn't vary very much between years. Whereas the melt rate varies between losing about the same, 200,000 kilometers squared a day, but it can lose 3 times more than that in some years. So massive change in the melt rate. We have a conceptual model of why Antarctic sea ice has a long growing period, but a fast melting period. Around Antarctica, there's a belt of low pressure that circles the continent. It's not an actual band of low pressure, it's rather made up by the tracks of large numbers of individual storms. I'll talk a bit more about these storms later, but at any one time circling the continent, I think if you stand anywhere between 50 and 60 degrees south, then if you haven't had a storm in a few days, there'll be one arriving imminently. So in this figure here, this band here is just to illustrate this kind of imaginary belt, which is a low pressure band made up of all these different storms traveling around. And north of this band, we have westerly winds that encircle the continent, and south of the band, we have easterly winds. Because we live on a rotating planet, winds traveling long distances, like those circling Antarctica, are subject to the Coriolis force, which in the southern hemisphere causes moving fluid to curve to the left. So westerlies, those around here, push sea ice to the north, and easterlies push sea ice to the south. And the 2 key places where this affects the seasonal cycle is when we start to get freezing and when we start to get melting. So when the ice starts to freeze in about March, the ice edge is inside of the circumpolar trough, so it's being affected by easterly winds. And those easterly winds are pushing the ice back towards the continent. So when sea ice starts to grow, it has to work against these easterly winds. On the other hand, when we start to have melting in November and December, and this is where the most rapid melting happens, the ice edge is outside the circumpolar trough. And so therefore, as the ice is starting to melt, it's aided and it's pushed back towards the continent by these westerly winds. There also could be divergence. These winds can help open up areas of dark ocean that warm fast and help to melt the ice faster. And in fact, this is something that we have been able to show. So we used model outputs to try to quantify the role of winds in controlling the slow growth and the fast melt of Antarctic sea ice. While we were able to confirm that divergence in spring does open up warmer water regions that help to melt the sea ice faster through this ice-ocean albedo feedback, kind of similar an extension of the ice albedo feedback that I talked about earlier. We haven't yet been able to quantify the role of winds in slowing the sea ice growth, and this remains an active area of research for our group. Unlike Arctic sea ice, which has declined crazily over the satellite record, on the whole, Arctic sea ice cover has been steadily increasing, which is quite interesting. These figures here show seasonal anomalies. So that's the difference in each season, how much more or how much less sea ice there was. And as you can see, there's quite a lot of variability from year to year. So some years we have quite a lot more ice, and other years we have quite a lot less ice. But despite the variability, you can see that there is an increasing trend throughout the data record. Between 2000 and 2014, this rate of increase accelerated to almost 5 times the rate observed from the start of the satellite period to about 2000. And eventually we hit this really record high annual mean sea ice extent in 2014. And what happened next was completely unexpected, and it took the research community by surprise. Over just 3 years, the annual mean sea ice fell to a record low, the lowest ever seen in the 40-year satellite record. This rapid decline stands in stark contrast to the overall increase that you can see in the record. And in fact, there still is a positive trend, even though there was that big jump. And another really interesting thing is that that jump in 3 years was similar in magnitude to the 30-year decline that we observed in the Arctic. The sudden decline in Antarctic sea ice was totally unexpected, and there have been a number of studies to try and understand why it happened. This figure here is from a paper that we currently have under review, in which we examined all the studies that have recently taken place to try and bring together an overall explanation of what caused the recent rapid decline. This pattern of change around Antarctica as a whole, this slowly increasing trend, masks regional variability, which you can see in the figures below. So this figure here shows the average sea ice concentration over a year, so the average annual sea ice concentration. And this one shows the change from 1979 to 2015. And you can see that there are areas where we have more sea ice and areas that we have less sea ice. This figure shows that the regional changes during the recent decline were almost opposite to the long-term trend. Nearly all regions experienced dramatic sea ice loss, in particular the Weddell Sea here. So this is where Shackleton got trapped and lost his ship. And it was only really the Western Ross Sea and the Indian Ocean where we didn't experience anomalously low sea ice conditions. The general consensus is from all of the research that's been done is that it was changes to the band of westerlies that encircle the continent. So those westerly winds that I was talking about before, they were the key player in driving this really big drop in sea ice from 2014 to 2018. During that time, really big easterly wind anomalies pushed sea ice towards the continent and created this exceptional reduction in sea ice. However, there's still really low confidence as to what the precise drivers of these anomalous winds are. We can say that these anomalous westerly winds were triggered by warm sea surface temperatures and very high rainfall in the tropical Pacific and Indian Oceans. So this is quite interesting. Changes at the tropics can drive rapid change in the Southern Ocean. This recent rapid decline was largely the result of naturally occurring variability, but the role of anthropogenic forcing can't be excluded and should be a major focus of future studies. Now, if you want to study sea ice, then you need access to an icebreaker. And our group has developed a collaboration with Marcello Vicky at the University of Cape Town in South Africa. And through this collaboration, we've been able to participate in 2 research cruises to the Southern Ocean at the generous invitation of the South African government. The first one was July 2017. During this expedition, it was a very special trip actually, because we went during winter. And this was special because not many people visit Antarctic sea ice in the winter, for good reason actually. The storms are immense. But this is also what makes it an interesting time to go there, to make really rare observations in the winter. The second cruise we participated in was just over a year ago. This is the spring season in the Southern Hemisphere, so spring 2019. And this was part of the SCALE project, the Southern Ocean Seasonal Experiment, which aims to study seasonal changes in the Southern Ocean. And this was a really great opportunity to make measurements in the sea ice because we had loads of stations. I had about 10 stations. This is the ice edge here. And we had about 10 stations in the ice where we could make measurements. And then on the way back, we came back right along the ice edge because there were other people on the cruise who were doing wave observations, as this was early spring. Our first collaborative research with UCT was looking at how intense polar cyclones can reshape the ice cover. Some of the most severe storms on Earth occur in the Southern Ocean, and some of these occur in winter in the Southern Ocean. This is an image of a storm on the 2nd of July, 2017. So this was during our winter cruise, where we headed from Cape Town and down to the ice edge, and we were probably just about here, just about to enter the ice edge as this massive storm hit. These storms maintain the low pressure belt that I mentioned earlier. So we've got massive storms that are continually passing around the Antarctic continent, and they continually shape the ice edge. We know that mid-latitude storms in the open ocean contribute to the infection of warm, moist air towards the poles because of the way they're spinning in the Southern Hemisphere. So you've got warm air coming from the north being brought down towards the pole. But in the open ocean, we do know that the net heat flux is balanced because the ocean gains heat in the warm sector and then loses heat in the cold sector. What we're not so sure about is what happens when these polar cyclones land on ice. So similarly to a mid-latitude cyclone arriving in the ocean, we have warm air being evected on the flank. And so this warm air is traveling over the sea ice, and we get a really big thermodynamic effect where this warm air starts melting the ice because it's much warmer air than the air around. And then on the opposing flank of the cyclone, we're getting sea ice being dragged out towards the open ocean. So you get quite a big change in the ice edge. This is the ice edge here, with warm air being pushed in here, pushing sea ice back, but also melting it through the warm temperatures. Cold air being pushed this way and pushing sea ice out to the ocean. And in the middle, where all the craziness is going on, we've got massive winds, we've got massive waves being generated, and that affects the sea ice concentration in between. After the passage of the cyclone, the air temperatures return to freezing and the ice continues to grow again. But what we're not sure about is what the net impact is. And what we didn't have on this trip was a measurement of the fluxes that were happening. And this is an area of research that we're very interested in, to try and understand, is it net zero like in open ocean cyclones, or is there something else happening as these cyclones land on the ice? So I said in the last slide that there was large waves propagating quite far into the sea ice. How do we know that? Well, on this cruise, our centre actually deployed a couple of Waveboys on a couple of pancake floes in the marginal ice zone. And these are our Waveboys here. This is one of my colleagues, John, and he's enjoying some sunshine while we test out the Waveboys. One of the bonuses of joining these research cruises on the Agulhas is that you get to leave and depart from Cape Town, which has one of the most amazing ports in the world. So this is us enjoying Cape Town just before we set off on the cruise. I've added this photo in mostly to show that I actually occasionally do some work some of the time. This is a photo of me sealing up one of the buoys before we deploy it. So we deployed our buoys onto pancake ice floes in the middle of a storm in July 2017. This is one of the floes that we deployed on. This is the buoy sitting there, taking its measurements, measuring how big the waves are. This big main photo here was actually taken by John from one of these cradles. So he's in a cradle similar to this, hanging off a crane off the edge of the ship, and he's heading down to deploy our buoy. He took this photo using a GoPro, and GoPro cameras remove movement from the image. So you can't tell from this photo that actually this whole ice area is being subjected to massive waves coming through. We had waves of over 7 meters moving through the ice during the time of deployment. One thing I do want to point out with this photo is that the ice cover is 100%. So we have 100% white. So if you're looking at that from a satellite, the satellite will tell you that this is full ice cover. But this is very different from 100% pack ice cover that you might normally expect your 100% ice to be. This is about 60% pancakes, these big pancake discs. And then in between, we've got all this frazzle ice, which is that kind of slushy ice that I showed you before. And this sort of 100% ice cover behaves very differently to a thick sheet of ice. This is just a photo of the wave heights that we measured with the buoys, just to prove to you that even though you can't see it in the photo, it was quite a hairy deployment. So you can see we deployed just here on the 4th of July, and you can see that we deployed right before the peak of the storm. So the waves were up to 7 to 8 meters. During this deployment, not only did we get point information on waves in the Southern Ocean, which we contributed to a global database, but the information from our buoys also provided an important component to some research that was led by Albedo, also on the cruise, who's based at the University of Adelaide. This was the first study to measure drifted pancake ice flows and wave activity during a series of intense winter polar cyclones. Pancake ice flows in the marginal ice zone. So the marginal ice zone is that area that's really subjected to change by waves, it's impacted by waves. And so even if we have 100% ice concentration, we can have very mobile ice field. So remember that photo that I showed you a couple of slides back. And during our deployment, we measured a maximum instantaneous ice drift speed of 0.75 meters per second, which is far exceeds previously reported values for the Southern Ocean. One other surprising finding was that wind was the dominant forcing for drifting ice. So even though we measured really strong waves in ice, so think back to the nearly 8-meter waves that we recorded, and this was 100 meters in from the ice edge, a free drift model based on the wind actually predicts pancake ice velocities very, very well. Our most recent work involves trying to better understand fluxes over sea ice. If you think back to the work on polar cyclones that I talked about, we were really missing important information on heat fluxes in order to understand how it is that polar cyclones arrive on sea ice. There's actually a really big knowledge gap on sea ice fluxes in the Southern Ocean because of the challenging conditions, the really sparse spatial and temporal coverage of any observations. So our aim on the last cruise that we went on was to try and measure these fluxes on the ice. So to do that, we put up a mast which has an anemometer to measure wind speed, a hygrometer to measure water vapor fluctuations, and a radiometer to measure upwelling and downwelling radiation. So we put up the mast on the sea ice, left it for a few days and came back, luckily found it again, collected it and brought it back. We also tried to measure, using the same equipment, we tried to measure the fluxes over different types of sea ice. This is still a work in progress and we're fine-tuning our methods, but watch this space for future insights, and we hope to be measuring more fluxes in the Southern Ocean soon. With that, I'm coming to the end of my time. I've packed quite a lot into this talk, and I'm just going to leave you with a few takeaway messages. The first is that observing sea ice is really difficult and quite dangerous. We need international collaborations to provide resources such as satellite missions and research vessels to make on-the-ground observations. All nations are affected by the consequences of changing sea ice, and even though polar regions seem really far away, they play a key role in driving global climate. Sea ice is a story of change and transformation on daily, seasonal, and decadal timescales, and I'm sure that as soon as we have a long enough record, we'll find that changes a lot on multi-decadal timescales. Arctic sea ice is rapidly declining, and it's likely that we'll see an ice-free Arctic Ocean in the summer within the next few decades. However, Antarctic sea ice is a different story and remains an active area of research. And this is very much needed so that we can make robust projections in the future. Think about how much area that Antarctic sea ice covers. And finally, I really hope that I've managed to convey the message that sea ice might seem far away if you live in the UAE or wherever else in the world you might be joining this webinar. But whatever happens in the poles certainly doesn't stay in the poles. And it's of concern to all of us, wherever you live in the world, to know how sea ice is changing. And I'll leave you with a photo of some Adelie penguins that we saw on our last field trip. All of the research that I presented here has been funded by the Centre for Global Sea Level Change, part of the NYU Abu Dhabi Research Institute. And the opportunities for the research cruises were provided by the South African government on board their research vessel, the Eayrs 2. I'd like to say thanks to my many collaborators around the world, especially David Holland, Marcello Vicky, Alberto Alborello, Marilyn Raphael, and Zishen Lee, without whom much of this work would not have taken place. But there are also many, many others. And I'd like to especially thank my colleagues at the Centre for Global Sea Level Change who have helped me deploy equipment, analyse data sets, provided moral support during those challenging moments in the field, and given feedback on my research talks and manuscripts. And with that, I'll be delighted to take any questions.
All right, thank you, Claire. It's kind of an interesting experience giving these virtual talks. You really, I can see there are a lot of people out there. There's like about 90 people online, which is great. I really enjoyed your talk, and I'm sure those folks did as well. Claire, there are several questions in the, can you see the question and answer?
Yes, I can.
So, sorry about the knocking. I'm gonna try to mute myself in a minute. That's the wall construction. So you start with the first one, the anonymous one. Can you kind of read that out and then respond to that one?
Yes, so we've got a question here that says, climate change is clearly a hotly debated issue that may cause significant irreversible damage if we let it. With the current state of sea ice in polar regions, at what point should we shift the focus from prevention to adaptation? Oh, that's a very good question. I think that they should both be considered together because we're still very unsure about how fast things might change. And I think it makes sense to be looking at both, researching as much as possible as to what you can know about prevention and adaptation. I think realistically, we have a lot of people living along coastlines around the world, and it's going to be impossible to move everyone. So there will have to be some sort of adaptation.
Okay, the next question, Claire, from Science Cathedral, about really timescales, about the fact we have short records and we need long ones. Can you read that one out and answer that?
Yes, sure. So we have a question that says, when you measure the trend increase rate from 1980 to 2000 and then 2000 to 2014, are the rates robust as you change your window of observation? Is the time window of 20 years big enough to capture climatic variability, which should span time periods of the order of 100 years? Yeah, really good question. We are limited with our sea ice record in that it's only 40 years long. And most research to date has had to focus on daily, seasonal, and interannual timescales for that reason. I would say no. I'd say we need a longer data time series to really understand what is happening to sea ice. I think in the Arctic, there's a clear downward trend, and I don't think having a longer record would change that information. But we have a real lack of understanding in what is happening in Antarctica, and it's incredibly hard to separate out what is natural variability because we just don't know how big that natural variability is. And I think we definitely need a longer time series in order to look at this. People are trying to increase the length of the time series. So as I mentioned, there are now, we're starting to pull together paleo records. The disadvantage of a paleo record is, again, it's just from a point in time. So it has a similar limitation of collecting sea ice in the field where you're just going into one place. There are also new techniques being developed that use statistical analyses to try and link sea ice cover with other climate variables, and some other climate variables we know quite well going back through time. So that could be another way of extending the sea ice record. But yes, we need a longer record, and perhaps waiting for it to increase through the satellite time is maybe not appropriate. Maybe we do need to look at ways of trying to extend backwards.
Okay, I think so. If you follow along the questions there's a nice comment, and the next one is Science Cathedral. Will the slides be shared? Yes. Okay. Layla. So do you see the one from Layla?
Yes, I've got a question from Layla that asks, on the flux mask, what does the radiometer indicate? So the radiometer has two sensors. One's looking up, one's looking down. Actually, it's four sensors. There's two upward-looking ones and two downward-looking ones. And we're looking at how much long-wave and short-wave radiation is upwelling and how much long-wave and short-wave radiation is downwelling. So from that, we can tell how much how much of the solar radiation is being reflected, so we can have a very good understanding of the albedo.
Okay, next is about solar activity from Science, and you can see that question about the solar activity, and you want to address that? You read it out, please.
Yes, so the question about solar activity, could the increased solar activity be playing a role in the warming up of the planet? And do we have models to forecast how increased radiation from the sun will change in the sea ice patterns? So solar activity has played a role in the climate dynamics of our planet throughout history. And in fact, some of the changes, as I was talking about, from greenhouse to icehouse, are due to changes in solar activity, but also orbits of the planets and how close and how far we are for the sun. In the warming up, if you're talking about the recent warming up that we've had over the last 100 years, then no, that's not driven by solar activity. That's definitely driven by increased carbon dioxide in the atmosphere. Solar activity happens on quite slow timescales. So when you have very rapid change, that's not due to solar activity. Okay. Do we have models that forecast increased radiation from the sun? Yeah, well, we have models that understand what the sun's output is and how how our planet is changing in relation to the orbits of the planet. And so we do understand how radiation does change from the sun.
And the whole thing with space weather is an emerging, exciting field. The next one is from Anonymous. How can people help, I guess, is it more of a policy question.
Yeah, okay. Well, I'm reluctant to answer a policy question, seeing as that's not my area of expertise. But I mean, I guess by giving this talk, what I'm wanting to do is raise awareness of how ice is changing in the Arctic and Antarctica. Donations to organizations, I guess, is always a good thing. Maybe look into the organizations you're donating to. Changes in one's carbon dioxide footprint. Again, definitely a good thing to look into. Probably needs to happen at the level of government to make big change. But yeah, I can't really comment too much on science policy.
And the next one is, later, can you provide some links on statistical methods about how to extend the historical record?
Yes, I can find out how to share some links on that. Yes, definitely.
Okay, and next one is very interesting as well. How does sea ice melt affect global warming? It's kind of the opposite, the vice versa.
Yes. So if we have sea ice melting, then we've got less radiation being reflected back to space. And so it actually increases the ice melting. So this is the feedback mechanism that I was talking about. So as the globe is warming, as we get warmer temperatures, with less sea ice, we get more warming. And in fact, you can see that particularly in the Arctic, which is losing sea ice. It's warming 3 times faster than the rest of the planet for that reason.
And one of your colleagues, Shi Chen, and my colleague, he has just put together some work on this topic, which is fascinating. So the Arctic sea ice change that you described, when that's put into a climate model, it actually changes the atmospheric circulation and it reduces the ice over the Himalaya, which is absolutely amazing, these amazing teleconnections. Next one is from Anonymous. Can you see the one at 1026?
Yes. So how Greenhouse Earth, Icehouse Earth, and Snowball Earth changed? Were these changes related to sea ice changes? Sea ice cover played a role in that, and certainly as you go from Icehouse Earth to Snowball Earth, that is very much an ice albedo effect. But the changes from Greenhouse Earth to Icehouse Earth are largely related to to how the continents are spread around the globe, and changes in the space changes in the continents change volcanic activity significantly. And so that really plays a big role.
From Robert, the one on biology.
Excluding temperature, is sea ice melting affecting microlife? Yes, it is actually. In the Arctic, they're finding that there's actually been an increase in primary productivity because of there being less sea ice. There's actually more light reaching the ocean. So one of the perhaps gains of losing Arctic sea ice is an increase in productivity, which has also been shown to have a positive effect on some of the whale populations. So the whales in some places around the Arctic are still declining. So not all of them are winning in this respect, but those that feed off phytoplankton in the center of the Arctic are actually increasing in their populations.
Next one from John Burt on global teleconnections and your work relating to Marian and Shi Chen.
Yes, so we mentioned the influence of the Pacific Indian Ocean temperatures. Yes, yes, we're working with atmospheric flows. So yes, so Shi-Chen Li, who's one of my collaborators based in China at the Institute of Atmospheric Sciences, he's doing a lot of work on looking at how teleconnections, so how things happening in the tropics affect sea ice at both poles, but then also how things happening at the poles can then affect things elsewhere. As David said, how you can then get reduced ice in the Himalayas just because you've got less ice in the Arctic. And we're just really starting, I think, to understand how it's really not a polar issue. Things happening at the poles is affecting all kinds of things around the world.
The next one from PS in regards to how information from the past from an ice core can be used for the future.
Okay, yeah, so The ice record gives us insight into the past.
Yeah, just read the question out so everyone can hear it. Yeah.
The ice record gives us insight into the past, however limited, as you mentioned. What are the techniques used to provide insight into the potential futures from the ice record? And what are some of the major challenges for doing so? So to look at future change, we really need models. I mean, to have models that work well, we need observations, and we probably need a longer observation record than we do, because models, the Arctic, we can predict Arctic sea ice change pretty well, but Antarctic sea ice is still very, very difficult for us to even reproduce the historical record. So we do need models, and the major challenge is making sure that we have enough processes in the models and making sure that we understand past change so that we can predict future change.
And then the next from Anonymous.
So what possible measures can be taken to improve sea ice growth? So what we want to make sure is that we have a cool enough winter so that the sea ice can form. There's been actually some research into, I said there was a little bit of a debate going on in the scientific community right now about whether it's possible for us to be moving into a hothouse Earth situation. And some of the modeling studies they've done, they found that actually it's fairly easy to reverse ice loss in the Arctic in a model after about 50 to 100 years. So that might not actually be an irreversible change. We're not so sure about Antarctic sea ice, because if you warm the Southern Ocean, then that's a lot of warming that would have to be taken out of the system. But yeah, it's all about, sea ice needs cold temperatures to grow.
Okay, the next one from Alan Wang.
How much sea ice change is related to human activity versus the natural cycle? I think it's been pretty comprehensively shown that the decline of sea ice in the Arctic is very much related to anthropogenic change. But there's not yet any evidence that change in the Arctic, in Antarctica, is related to human activity. We saw a really, really big decrease in Antarctic sea ice from 2014 to 2018, but that's largely been shown that it's probably, that change was related to natural variability. But certainly Arctic sea ice change is definitely related to human activity.
The next one from Science Cathedral, and it's about sea ice melt, decreasing albedo. Can you read that one out?
On the topic of the effect of sea ice melt on climate, wouldn't the decreased albedo of the Earth's surface lead to a global drop in temperature instead of warming? What is the relative timescale between ice melting and freezing due to massive albedo reduction?
I didn't understand that. If the albedo drops, the planet becomes warmer.
Yes, if there's less sea ice, then you get warming, and so then there's less ice. So then, yes, so it's a feedback effect. So less ice actually means decreased albedo means you get warming.
Okay, next one, Anonymous.
You mentioned the effects of Arctic amplification. What are the risks of polar amplification at the South Pole? We haven't yet seen polar amplification at the South Pole. This is likely to be due to the fact that of its geography. So Antarctica is a continent that's surrounded by oceans. And I talked quite a bit about winds that encircle the continent. And we also have currents that circle the continent. And so there's an ocean and atmosphere boundary between Antarctica and the rest of the world. And I guess that is somewhat making changes slower, although there are these teleconnections that we mentioned before that can bring changes in the tropics to Antarctica. The main reason that you don't get this amplification is that we haven't had a decrease in Antarctic sea ice yet. So over the record, it's been slowly increasing.
And the next from Anonymous about human activity.
So Arctic sea ice decline is definitely related to increasing temperatures due to global warming. Antarctic sea ice change, we don't really know.
From Robert about the CO2 levels back in time.
Oh, that's a good question. I'm not actually sure what the spike was, the CO2 level was, but it's thought that that was to do with a volcanic eruption. It did bring temperatures actually up to about 10 degrees warmer than today, which is pretty impressive actually.
Anonymous.
How much does sea ice melting affect ocean salinity, and what impacts would this have on ocean currents, marine life, and coral reefs? This is a great question. So every year we get sea ice melting, and when the sea ice melts, that means we've got more fresh water. So as sea ice grows, I said it ejects salinity, and as it melts, that's fresh water that's being added to the water column. The really main thing about sea ice growth actually affecting ocean salinity, and this is another big way in which sea ice can really impact global climate actually, is when you have sea ice growing and you have the salt being ejected into the water column. Salty water is much more dense than fresher water. And so when you have this very salty water around the areas of sea ice formation, that drops right to the bottom of the ocean. And there are a couple of locations, one up in Greenland and one in Antarctica, where we get this, it's called deep water formation. And that is the start of the currents that travel around the globe. So sea ice forming and melting actually plays a big role in ocean currents.
Yeah, and also, as you're saying, the global conveyor belt, the movement of water around the planet is driven by salt density differences. So it's all connected. Next one, Anonymous. Do you foresee impacts of restricted human activity on many fronts, including less emission? Since the pandemic started, we hear about less pollution. So pandemics, pollution, and climate.
Yeah, okay. So this is not a major area of research on my point, so I don't know for sure, but I do know that they have seen less emissions over the last year. I think I saw a recent article that said they thought actually there's been a smaller drop in CO2 emissions actually than they thought there might be. So yes, the pandemic has definitely had an impact and it will have an impact on global climate. But I think already the impact is much less than it was, say, in March and April of last year.
Next, it's about, I don't know if you heard it over there, but there's, with the new administration, whether or not Alaska will have oil drilling going on and off. So the question is about oil drilling in Alaska and what it has to do with sea ice.
I don't actually know what the effect of oil drilling is, but obviously if you then use all that oil and then we have increases in carbon dioxide, then that does have an effect on certainly Arctic sea ice.
So we're doing fine on time. Those have been really excellent questions, and your answers also, Claire, have been right on the mark. So a comment I would pass along too, which I think was in your closing remark, is that two things. One is people think ice is, the poles are far away, and they're not. And I think you brought them closer. They're not very far away. A trip from New York to Abu Dhabi is no different than a trip from Abu Dhabi to the poles. So there's that part. And the other part is, I think people are confused or not clear that we're never going to understand climate change in the UAE unless we understand climate change in the polar regions. And we're never going to understand climate change in the polar regions unless we go there. So otherwise, there's just no way to project climate change. So I hope people get their heads around that and why you're doing what you're doing. And Claire, do you want to wrap up and then we'll call it a day?
Okay, well, yeah, well, thank you very much, everyone, for listening to our talk. I hope that you took away that important message that the research that we're doing at, certainly I'm doing a lot of research in Antarctica, and the work that others are doing in the Arctic is really important to how climate is changing all around the world. And although they seem like really far away places, it is really important that we study these places so we can find out how sea level is going to change wherever you are locally. And everybody lives somewhere close enough, I'm sure, to a coastline to appreciate that. And the other thing is that these are actually really big questions that we're trying to answer. And they're probably bigger questions than one research group, even one nation can maybe respond to. And I think that collaboration is really, really needed. The international community does need to get behind these programs and make sure that we can get to the places that we need to get to understand what's happening at the poles. Thanks very much, everybody, for listening to my talk.